Okay, well, let's start looking at the calculations for our acetone lab. The molar mass of acetone. I know it says here the molar volume, but it's really the molar mass of acetone. So I've taken that lab that we just finished, uploaded all of the data, and so you can see it here. The only thing I added to this list, we have the mass of the flask empty and with water. We have the mass of the flask and the attachments and the liquid that was condensed. We have atmospheric pressure. I also used the vapor pressure of acetone at room temperature, and we're going to need that because one of the things we find is that acetone has a vapor pressure. So anytime it's in the liquid state, the vapor pressure must be considered. And so I looked that up. There's an actual place where, again, it's a constant. So you have to look up the temperature and the pressure of acetone, which just like the vapor pressure of water is temperature dependent. I have room temperature, the boiling temperature of water, and acetone itself is CH3COCH3. And so I can take that formula, add everything up, and I get an actual molar mass of 58 grams per mole. Well, I also want to now then kind of move to our calculations, and I'll look at trial 1. You can then do your own calculations for trial 2. So here we have the first one. It says the mass of the air in the empty flask. See, one of the misnomers when we say that a flask is empty is that it's really not empty. It's a flask that's actually full of air. It's just not filled with any liquid. So what we're going to do is figure out how much air there is in an empty flask. So we need to consider, and this is what makes this lab so hard. Normally we would just say, MM equals MRT over PV. I mean, I have M, I know P, I know T, and I know V. We could just plug that in. Well, we really should account for some things that are really taking place. And that's what makes this lab a little more challenging than most. And so to find the mass of air in the flask, mass is equal to density times volume. Now, when we talk about the density, this density would be the density of air, which is 1.29 grams per liter. And then the V is going to be the volume of the flask in liters. So we'll go back to the top and we'll grab those numbers real quick so we can get that. That flask itself was 207.44 when filled with water, minus 61.917 when empty. And so the volume of the flask, 207.44 minus 61.917 is 145.523 milliliters. And you'll notice for the sake of making things as easy as possible, I did eliminate our plus minuses for this lab. I know that probably really hurts you. You're probably thinking, man, I really wish I had a plus minus to deal with. I just thought that we'll just take that one thing out of this lab and try to make it a little bit easier for you, although there would be an uncertainty involved in this. But, for our sake, let's just for this lab, put it off until the next one, if that's okay with you. If not, we can put it in there. I just thought that might be a help for you. So let's take that volume in liters, and let's multiply that by the density. And so the mass of the air in the empty flask came out to be, let's see, sig figs here, 1, 2, 3, 4, 5, 6. We got 0.18725 grams. Now again, with uncertainties, we would be able to get something that was maybe less digits, but that's okay. At the end, this will all come out the way we want it to. So we'll put that up here as our, I don't even think that's even one of our things. The volume of the flask is, so let's put that in, 145.523. Okay, and so now I have the volume of the flask. I have the mass of air in the flask. Okay, the next one says the mass of condensed liquid corrected for air. Well, let's go back to the mass of the condensed liquid. We need that first. Well, let's write this in here because what I need is the mass of the condensed liquid plus the mass of the air in the flask. Now you need to say, whoa, 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 what are you doing? You're adding the air in here. Okay, let me explain why I have to do that. Since the flask was supposed to be an empty flask, well, it is an empty flask, but it actually had air in the flask, we need to either subtract the air out of the initial reading of the empty flask, or we need to add this back into the liquid. So we would either have to go back to our flask, that 61.917, take out of that 0.188, or we just add that value in from what the air is, and you'll be able to get a corrected mass of the liquid. So let's go up here and let's find the mass of the liquid before we correct it. And so we're going to take the 62.851 minus 62.590. And I got, oh wait, hold on. Yeah, flask and the attachments. Yeah, 0.261. Okay, 0.261 grams. Now, again, that's the mass of the condensed liquid. Our second calculation here is the mass of the condensed liquid corrected for the air that enters the flask. So we take that mass of condensed liquid, 0.261, and instead of subtracting out that flask in the beginning, taking the flask and removing that from that 62.590, let's just add that air in, 0.187725. And so we get a true mass of 0.449 grams. We'll go to the third decimal place. So that is the mass of the condensed liquid. Okay. Well, let's see. We're going to kind of get down to some of these other ones. And so I guess when we look up at our chart here, it says mass of air that re-enters the flask, corrected mass of condensed liquid, actual mass of condensed liquid. So let's go down and let's put that in here. That corrected mass is what we just solved for. So let me put that in, 0.449 grams. Okay, our next one, number 3, is the mass of air that re-enters the flask. Well, you see, here's what happens. Once we actually start heating the flask, and we talked about this in the intro to the lab, when you heat the flask, you force all of the air out as well as all of the excess vapor. When you condense the liquid into a gas, you'll notice that the vapor pressure there is much, much lower than atmospheric pressure, so pressure outside greater than pressure inside. Air will force its way in until the pressure inside and outside are equal. And so, to find out how much air re-entered the flask at the end when we massed it, we take the percent of air in the flask times the mass of air when the flask is 100% full. So again, as we're condensing that acetone, the acetone condenses, air rushes back into the flask until the two are equal to atmospheric pressure. So how do I do that? Well, I'm going to find the percent of air. How do I do that? Well, I'm going to take the partial pressure of the air all over atmospheric pressure. Now we think, how do we get that? Well, the partial pressure of the air is found by taking atmospheric pressure minus the other gas that's in there, the vapor pressure of acetone. Again, all of that over atmospheric pressure. So atmospheric pressure in this case, 754.2. Vapor pressure of acetone, 188.462, all over 754.2. I don't even think I need that. Let's leave it as a percent for now. Oops. So let's see. We have 754.2 minus 188.462. Oh, wait. I got some weird stuff on my calculator going on here. Hold on. 754.2 minus 188.462. This number, just so you know, comes out to be 565. Hard to read that. 0.7. I'm going to take that. Whoa, that doesn't seem right. How in the world? Yeah, I'm sorry, that's right. I thought I saw a 7 in there, my fault. Yeah, that is correct. Divided by 754.2 times 100. So what I end up with, I get 75, so the percentage of 0. Let's see my sig figs here, 1, 2, 3, 4, 7, 5, 0, 1. So that flask has actually 75% of it is air. Now, I take the mass of air that would fill the flask if it were full, the empty flask. And so I take that 0.7501 times 0.187725. Oops. So 0.7501 times 0.187725. And to 4 sig figs, I get 0.1408 grams. That is the mass that will re-enter the flask. So we go up here, and we put 0.1408 grams is back in. So here's what's happening. We took an empty flask, and we accounted for the fact that it actually has air in it. That allowed us to find the real mass of the condensed liquid. The problem is that condensed liquid is a condensed liquid plus air that re-entered the flask. So now we must consider all of those things together to find the actual mass of the condensed liquid. It was the mass of the corrected liquid minus the mass of air that re-enters the flask. Mass of the condensed liquid that we corrected for the air in number 2, that's where this comes from, that was 0.449 minus the air that re-entered, 0.1408. 0.449 minus our answer, and we got to 3 decimal places, 0.308 grams. That's the mass of the actual acetone taking the air out of the equation, 0.308 grams. Okay, so I have that in there. Now what do I do with the fact that I have the mass and I have, it looks like everything else? Oh, This is the pressure of air that re-enters the flask. We have that. We actually solved that down here. That's our 565.7. Okay, we actually calculated that already. That was taking atmospheric pressure minus the vapor pressure of the acetone. Molar mass of acetone. Okay, well, MM now equals MRT all over PV. And we did all of that work to get M, 0.308. R, 0.0821. T, now this is where it gets tricky. The point where the pressure inside and outside are equal for the acetone, not the acetone and the air, was the boiling point. So this is our, the M comes from number 4. The temperature is the temperature of boiling because that's where the pressures are equal. Equal to atmospheric pressure. When the pressure inside and outside are equal of the acetone is when they were at when it was at the boiling point. And so the boiling point was 99. 372.0. All over P, atmospheric pressure. Remember, this has to be in atmospheres. 754.2 all over 760. And the V is the volume of the flask, and we found that earlier. Let me see if I can find my volume here. There's 0.145. 523. Boy, would this be overcomplicated with our uncertainties. I'm sure that many of you are thinking, I wish we had uncertainties. So let's take our temperature times 0.308 times 0.0821 divided by 754.2 multiplied by 760 divided by 0.145, 523. And the answer I got through all of that to 3 sig figs was 65.1 grams per mole. And I'll tell you what, that's a pretty good number compared, keeping in mind how we had to do this in my office. So 65.1 grams per mole. So what do we do for percent air? We don't need relative air, right? We got rid of the uncertainties for this one, just to kind of help you out a little bit. So we're going to take the average molar mass of acetone minus 58 all over 58 times 100. Everything else is fairly self-explanatory. If I go back to our data table, trial 1 is done for you. All you need to do is complete trial 2. You don't even need to do this relative error. You can just cross that out. We don't even need to do that for this lab. I mean, if you want, I can give it to you. You can figure all of that stuff out. But I thought all that's going to do is further complicate things for us. Okay, I want to do this as easy as possible. Hopefully that makes a lot of sense. Remember, you can ask me any questions. I will be online today, which is Friday, or email me. No problem at all. So calculations, you're showing me an example of those here. You'll need to do both trials. Complete trial 2. You need that for your average, and then complete the 3 questions that go along with it, which we should be able to get out of our pre-lab. Okay? Again, if you have questions, ask. Hey, this was a fun lab. See you tomorrow.